Right, morning. Um, so um, so this is going to be. I apologize. This course is taking a while, and so after 20 lectures, we're back to square one. And the square one, if I may remind you, what was that? The square one is what. Go back all the way to the first lecture. We recall the setup was something like x. This was maybe approximately was moduli space vacuum in a very in a supersymmetric with extended supersymmetry in a SUSY um, theory, 2+1 dimensional theory. And so at large scales or in infrared, we were thinking of this theory as kind of theory of modulated vacuum. So you have a map, theory of maps, F to that target X. So you were so I remind you the setup was that, well, at large distances, since we're interested in indices, we might as well think of what does the theory does in the infrared, and so then you can think of this at every point in your space, you already have a certain local vacuum established, so you have a map. And then moreover, since we have an extended supersymmetry, only supersymmetric configurations will contribute to the index, and so this would be supersymmetric will require roughly. So we can arrange that supersymmetry so that this is holomorphic for a certain change. So it has for a certain choice of complex structure in the domain, and we have it in the target. We already have it. In fact, we have almost like a hyperkähler structure in the domain in the target. And so this is we would like we'd like a supersymmetric states in this theory. Be roughly moduli spaces of objects like this. So we have a Riemann surface C and a holomorphic map to X. So I described it already. Is that approximately? And then on this we need index sheaf. Remember, the discussion from lecture 1 was that if you want an index of an operator, that in fact first you get a K-theory class on the manifold on which your differential operator acts, and then you can push forward of that index to the point so you get the index of the differential operator. So that index sheaf, well, we would like it to be something. So if I remind, so this is like the index. So it should be like the index. Yeah. Should be like the index sheaf for the Dirac operator. So in particular, if if I e.g. for a Kähler manifold, then the Dirac operator that this is the d-bar operator acting from operating in the or d-bar plus d-bar adjoint operating in, you take the canonical, this canonical of M, square root, tensor the direct sum over I omega 0 I of M. These are differential forms that are only in anti-holomorphic variables. So d bar acts on this, and the even and odd. So this is depending on whether this I is even or odd. We get the even and the grading, the fermionic grading is whether this is even or odd. And some model on this, we would like it to be, if you some modeled on this, you would like this to be the index sheaf. I would like it to be kind of like the virtual. So if you think about the construction of the virtual structure sheaf, that would be kind of like the virtual. This is this part. But then it has to be twisted by the square root of the virtual canonical. So virtual square root. And what is this virtual canonical is, so virtual, this comes from abstraction theory. Was explained by Melissa last time. This originates from abstraction theory. Which has, for instance, has virtual tangent space, which comes from deformations minus abstractions, the map. So which we can represent by, which is in the K-theory class, this represented by difference of the vector bundles, like in Melissa's lecture. So I think E naught and maybe the duals of E naught and E1. And so then the determinant of that is the virtual. That is the virtual canonical inverse. So maybe determinant of that inverse, that's the virtual canonical. It's a line bundle. There is no a priori reason, so we'll talk about it maybe later. There is no, in this setup like this, there's no a priori reason for the square root of that line bundle to exist, but maybe moreover, there is no real reason. So if we would like to compare, so formally, so this is deformations come from deformations. If we want to compare to a Kähler manifold, then the deformations should be compared with the tangent bundle of M. And the abstractions, well, they should be so more formal. Maybe I'll write it like this. So what's the virtual or virtual? Well, if my deformation space is smooth and the abstraction is an actual bundle, then O virtual, that is that's kind of O of the deformation space. Tensor, you have to put the alternating sum to exterior. So just Kazul complex for the Kazul complex for, so this is the Kazul complex for abstractions. So being abstractions dual. Right? And so if you want to compare with this formula here, then the we see that the anti-holomorphic forms by the metric that is dual to the holomorphic forms, and so this altogether there should be the statement that abstractions should be about the dual to the deformations. So in particular, so that's the condition we want to impose. So we want something like that. But that's this duality. It's hard to achieve that duality to be exactly right. So maybe it's okay. So we can. So okay. Also okay. If this space that is not exactly true, but maybe true up to tensor with something that we control. If we can control, meaning of some geometric input, we can. It's in our hands. We can put in the integration of all the characteristic sign, so that to make the theory self-dual. That's okay. And observe heuristically that if abstractions are dual to the deformation, then the determinant, so in particular the determinant, so this would imply that the determinant, okay, virtual, that is the determinant of abstractions square, because the dual spaces have the determinant dual inverse. So that makes sense that that would actually, the square root would be, we would be able to extract the square root. It doesn't prove that we can extract the square root, but because abstractions, so when you talk about virtual classes, it's always good to imagine that you have a smooth space and a vector bundle, but in reality, it's not what you get, and so it requires certain proof that the square root actually exists. So to summarize, we would like, what we want, moduli space maps So with perfect abstraction theory, that is almost is not a technical term, but I'll explain what it means. Almost self-dual means that we can achieve self-duality by inserting other things in the integral. And then, of course, we also want it also only be compact, means, or algebraic geometry and algebraic geometry will actually like it to be proper. Well, it can't really be proper since X by itself is not compact. But maybe we would like if we have a map. So if I, for example, if I fix that so if I have a curve proper over what? So if I have a curve in X, the way I've written it, keep making it smaller and smaller. So then X, we can further map. X was, remind you that X, by the kind of X we consider, they are projective over affine. So there's some affine variety X naught, which is maybe a symbolical draw or some kind of cone. And so if I take the composed map here, since this is a complete curve and this is an affine variety, it will have to go to a point. And I would like that map to be proper, meaning if we fix where on the blowdown the curve goes, so assume the curve's connected, and if it's disconnected, maybe where each component goes, assume that we fix the fiber of this variety is projective variety, and we would like within that fiber we would like the map space to be compact. And the important observation is both of this not so easy to achieve, or at least not so easy to achieve. Actually. And so this is why is that? Maybe Andrei will take a, but there will be, we will succeed. Or people have already succeeded. So in many different cases, but maybe I'll explain the basic geometric ideas is that if you'd like to compactify the space of maps, then you will have to add maps which are not. We'll have to add. So to achieve properties, you need to add maps for singularity. Okay. So. Proper modules. Eh? To allow singularities. So this is the simplest possible situation. Well, suppose I have. So this is, I apologize. So some of you are experts in numerical geometry, but also I hope some people who are more of a representation theoretic kind of math physics interest, they might not might not have thought about this before, and so I'll give really baby examples. So suppose I can take P2, and my P2 could be sitting inside. So this could be sitting inside T star P2 if you want. If you want the kind of, so T star P2 is a very important variety for us. So P2 is an important variety for us. And then in P2, of course, we can consider a conic. Conic in P2. And then, so this is an image of a degree 2 map from P1. So if I have a, I'll draw P1. I'll draw P1 like that. Map f of degree 2. But if I have a family of conic, of course, a family of conic will degenerate to a union of two lines. Right? So there's somehow no way, and there's no way to parameterize a union of two lines by a map from this P1. And so what people do in the moduli space of stable maps, so in Gromov-Witten style modular spaces, what you will have to allow, even so we we map. So this is this. When you consider modular space of maps, you may decide that you're mapping from a parametrized curve and unparametrized curve. So there's some distinction. But so this curve is fixed curve for us. We don't need to consider. Well, we will eventually, but for now we can think of a fixed curve. Or we can think about them with moduli, but so this source might be fixed. So, but even if it's fixed, so even if the source is fixed, you might have to grow all this kind of bubbles. You can consider things like things like that. So you kind of cocktail like that kind, right? And so this would be a curve, which would be this would be this would be a curve that if you forget the map, then you will have to collapse. Then if we forget the map, then we'll have to collapse all these bubbles and we go back to. Okay. However, so this is all good from the point of view. This Gromov-Witten style spaces, they do have a perfect abstraction theory, but these bubbles, they really spoil. This will be spoiled self-duality for the best of spaces. And why is that? What is so if I study a map from my curve, make it a little smaller. I should have made this smaller. So anyway, so I have a map. And so I have a map f to x. And let's say, for the sake of the argument, let's say, well, not for the sake of it, let's say this Sx is smooth. Then takes a while, actually. I realize the internet must be a little slow. It takes a while for the letters to appear on screen. But anyway, let's assume X is smooth. Then what's the deformation? Then what's the deformation theory of maybe let's draw a picture. So what's the deformation theory of that? This is X. And this X is smooth. And then this is, I don't know why I made it so small. Don't need to be so small. So what are the deformations? And I'm not moving the domain right now. I'm just moving the map. And so if I want to know, if I want to move the map, then for every point here, so maybe I have a point and there's an image. There's an image in X. Then for every point here, I have to tell it where it goes. So the deformations, easy to imagine, the deformations, there are sections of pullback, maybe sections on my curve C of the pullback of the tangent bundle to X. Right? And then what are the abstractions? Well, you can think actually about the virtual class. You can think a little. You can think somewhat concretely. You can take your curve and you can cover it by two affine charts. So one affine chart would be. So let's see if I can still. So if I take my curve. And I remove a point, minus some point, so I can choose some point. My curve's fixed, so I might as well fix a point on it. So it's C minus a point. And then the other chart, I'll draw like a little hole here. Like a little hole. And then the other chart is a formal neighborhood of that point. Disk. And this is gluing over the formal puncture disk. So this glued over formal puncture disk. So either of two charts are affine varieties, and they're on a map from a affine variety. You can somehow deform any way you like. But then if you want to glue them over this formal puncture disk, there will be some. You can think of the fact that the virtual class as being some sort of intersection on that virtual some sort of intersection of two subvarieties on this this formal puncture disk. And so then means it has to be the case that the deformations you write in one chart and the deformation you write in the other charts, they agree. And that computation is really the computation of it's the complex you use to compute the cohomology of a bundle. So the abstractions means the fact that these two things will have to agree. The abstractions would be the first cohomology of that one, H1 of that. What I'm trying to say, so you can move. so you have like a check complex from two charts, and you can move in each chart. You can move any way you like, but then the fact that you move these deformations agree on the overlap of the two charts, that's like a check complex, and it's the check complex for this bundle, for the pullback of the tension bundle. And so now this is our X is always of the kind that this is, for us, it's always self-dual, because our X is like a symplectic manifold. So it's particularly the dual of the variety is the variety. I mean, the dual of the bundle itself, always. So for X of the kind we consider. And so then so what would be the dual of the abstraction bundle? Abstraction dual is the dual of the first cohomology dual. Maybe I should write duals for, since I also have pullbacks, maybe it's better if I write duals like that. Okay, so what's the dual of first cohomology? This is by Serre. Serre says that this would be H naught of, you take the dual bundle, but that is the same. Take the dual. And that dual you can remove, as I said, this is because bundle self-dual, but then you have to take the canonical. Right? And that canonical is the canonical of the whole curve. So this is, we need, means that this would be, we can't control. So this would be the kind of correction. So this would be saying, like, if I have a vector space, so if I'm asking for sections of a vector bundle, I've got, so this sections of a vector bundle and section of a vector bundle twisted by a point. So this is in canonical some divisor. So they just differ by evaluation at this point. So this is something we can control as long as we control the curve, the domain curve. So this we can control. As long as we can control C, the domain curve. But this is precisely the issue with this sort of Gromov-Witten moduli spaces, because if we go here, this effect, this bubbles affect the canonical bundle in unpredictable, in both predictable and basically unmanageable way. Now, when I say something is unmanageable, this means this is some statement, and this is and this means it's not a mathematical statement. This is strictly my personal opinion. Not a math statement. So it's been investigated by. So first of all, there is a. So this is there is a whole school of thought, started with Giventhal, that one in fact should study K theory of this Gromov-Witten type type moduli spaces, and so you're free to pursue. There's a lot of work there, and you're free to pursue work in that area. So I'm not. There's a paper by so good thing to look is that there's a paper by Henry Liu. So good place to good paper to read. By Henry Liu. So this is not how I spell Henry. That has a discussion of the issues that come up and trying to make that abstraction theory self-dual. And you can free if you want to pursue this, then there is kind of a basic challenge. In K-theory of this Chrome-Witten in K-theory to go with Chrome-Witten theory is to do the case when X is T star G mod B. It's kind of the basic element. So this is if you're and what you should get. So this should be some quantum integrable system that should give you, if you succeed, that should give you basically McDonald operators. Consistent with the fact that if I degenerate it to X, this means degeneration means that there's the parameter H bar, which I send to 0 infinity. So the one that scales the cotangent fiber, then I get to G mod B, and for this you get the Toda. This is for get the Toda. Well, strictly speaking, for Lagrange dual group, but it's and that is okay. So this is really proven by Giventhal and by Billy. So this is long time ago, but then the flavor of these two theories is very different. So one is well, one can talk about that more, but so there's some in for spaces like G mod B, there's G mod curves in G mod B is essentially a smooth space. So we're not talking about this kind of self-duality and other intricacies. So that's a different thing. It's like integrating over M itself as opposed to doing the Dirac operator on it. So this is anyway. If you decide to pursue this, maybe you should think about this question. And if you want to go that way, I recommend you read Henry Liu's papers first. That describes the issues. And so this is we're not going to do this. So we're not going this way in this course. Instead, we will talk about a different moduli space, and this already came up in Melissa's lecture and came up also previously, maybe in some. And so for us would be important. So this would be So what we will make use of, we will make use. So X was some space, but we will make use of the fact that this in fact comes from a gauge theory. And so then this means that X would be like, e.g., like an academic variety. And maybe I should, since I just have this on the whiteboard, I have this information on the whiteboard. This is maybe you should note that that T star G mod B is not an academic variety. For G not equal GLN or SLN. So outside of type A, it's not an academic variety, and so this is somewhat, it's not a new issue in integrable systems, that McDonald polynomials and other things in type A, they have features different from other type, even in other classical types. And here we have another manifestation of that fact, that our theory, for example, will cover McDonald polynomials of type A, McDonald kind of theory of type A, but will not cover other types. Okay, sorry, this is the state of the art at the moment. And so in particular, X is the stable locus in some side quotient stack in Bellroyd X twiddle. That's the corresponding quotient stack, and maybe in this case for an academic variety, that's you take the pre-image of the moment map and you divide it by the group G. So this is not the same G, whatever whatever group you use for maybe moment map for G. So this where G is a group that acts on some symplectic representation. And so this would be the Higgs branch of the corresponding modular vacuum for the gauge theory. The ingredients there are the gauge group, and this is X in some representation M, which is this is the matter. And then we have, since it's a representation, it's a symplectic representation, we have the moment map mu going from M to the dual of the Lie algebra. And this is for instance an academic variety is of that type. and so then instead of mapping to X, we would like to first think about what it means to map to the quotient stack. So we'll find. So the goal is that instead of mapping, and maybe it's just easier for me to draw another curve. Instead of mapping this to X, we will want to think, what is it? What does it mean to map to the quotient stack? And the singularities that we decided at the beginning that you have to allow certain singularities, and otherwise it doesn't work. and then you can't find a proper modular space, and the singularities will be not of the kind that the domain degenerates, which is we decided it's undesirable since it messes with the self-duality of the theory. But the singularity would be that instead of mapping to X to the stable locus, I occasionally go unstable. So that would be the idea. And so then what's the remind? If you were in the seminar, in the Skoltech seminar yesterday, we already had a review of what it means to map to a stack, but maybe I'm not going to assume that this is everybody learned that. And so maybe the first step is that what does it mean to so map, and then the first stack to consider is maybe point mod G. And so that is, if you unravel the definition, then this is the same. Let me make it smaller. So that is the same as a G bundle over my curve. Principle. So I have maybe a principal G bundle. The all copies of G, so it's a P. And okay, so this when we talk about principal G bundles, maybe you should discuss and what sort of topology we consider. Are we doing like locally trivial in the risky topology, dual topology, and so on and so forth. But here in this situation, we're like doubly safe in that if my group is GLN, then all these notions are the same, or products of GLN, all these notions are the same. And then if my domain is a smooth curve, all these notions are the same. In general, they diverge, but this is we don't have to discuss it here. So so this you can think of analytic topology, principal G. Okay, it doesn't matter. So so then right. So that was the definition of a map to a point. But now suppose I now map to some other space, maybe call it Y mod G. So if I take well, that would be this P plus. So first you get the principal bundle, but you also get a section of the associated one bundle over. So if you take P product over G with Y, this is a bundle over C. So you get a, so if you have a G bundle and J acts on Y, you can make a Y bundle and you take a section of that, right? For instance. Let G be, well, I don't know, C star or GL1 or GM, whatever notation you like for that. And then it'll be operating on Y, which is whatever CN or AN, whatever notation you like for that. Then what is that space? That space becomes a principal GL1 bundle is the same as a line bundle. So you get the line bundle space, the line bundle L on my curve C plus section of, well, what would be the associated bundle? That's just L copies. So if you take L direct sum n times. So this to say section of n copies of my bundle is the same as n sections, i.e. n sections of L. And so we this looks very classical, like maps to projective space, and in fact it does. So if I have a map from a curve C, well, it doesn't have to be a curve. I want to map to projective space with dimension n minus 1. Then what do? I first take, then this is given by a line bundle, which is map F. This is given by a line bundle, which is the pullback of O1. Right? So this is this map. So if there has some kind of coordinate, maybe call it x. So this map f of x would be given by n homogeneous coordinates, right? F naught of x, maybe f1 of x, f2 of x, so forth, fn of x. And these are on P1, on Pn, these are sections. The coordinates are sections, not functions. These are sections of the coordinates are sections of O of 1 on Pn minus 1. And so these guys are n sections of the pullback of this line one plus n sections of L. And then to be actually mapped to projective space, they not without what's called base points. So base points is where all of them, base point is where all of them vanishes, where f of x is equal 0, where all of them vanishes bad. So this is, in this language here, we can think of, if we translate to the previous language, then we think of Pn minus 1 as being the stable locus, namely where not all points are 0 inside C and modulo C star, inside that stack. Right? So if I'm mapping a map to that stack is so maps from C to that quotient stack, that is a line bundle plus n sections. And then instead inside here we have maps from C to actual projective space, it's the stable locus that is the same plus no base point. Right? And then what we would like, the kind of spaces that we would like to consider is some intermediate space where, so we decided that space is not good enough because it has, like, if I impose the condition that this something never vanishes, that this contradicts properness, because something, if in a proper moduli space, you cannot impose an open condition, something not equal to 0. So that's not good. But so there'll be an intermediate mass space, and this is called, for historical reasons, this is called Quasimaps. Or maybe stable Quasimaps. So you well, I don't know, you still write it. I guess we'll just keep the stack target. And that is, well, it's like this, but base locus, there's a mention. It can have base points, but it cannot be, not all of them can be, not all of them means not all cannot vanish identically, or cannot vanish if you have a and also if my curve is, since I'm eventually want to think about nodal curves, that's also a good idea. So if and disjoint from nodes and mark nodes of. So this is a very simple space if you think about it, because if you think what are the so this is the this is so this is because it's like over so much more simple than the space, much simpler than this thing. But okay, simplicity is not. So this is like, if I fix the line bundle, that would be just a giant projective space. If I fix a line bundle L, all I'm asking is, so if I fix a line bundle L, so for fixed L, then I get just projectivization of H naught of CL n copies. And projectivization is because a line bundle has an automorphism. I can't really fix a line bundle. Line bundle has an automorphism of scaling, and so that will act on this. We consider up to isomorphism, and so that will act also on sections. And this would be, so this is the way to write it out: is you take n copies of the sections and mod by automorphisms of my line bundle, which is C star. And then if the line bundle moves, then okay, that's a projective bundle over however the line bundle is going to move. So So this brings us to the definition of stable quasimaps from C to X, and this is all right, Y mod G so this is what? This is the following data. P, a principal called F, a principal G bundle over C. Then F is really a section of the associated Y bundle section. So you have a bundle. This is bundle over C, and you ask for a section. And then the condition that the base locus, which is what? Which is F inverse of the unstable locus in Y, this is finitely many points. So this is zero dimensional, or maybe finitely many, and the indisjoint. From nodes and maybe some other more. Max points of. Okay. No, we didn't think about mark points yet, but and we didn't have nodes yet, but in the future we'll have to think about them. And so what would that be for the Hilbert scheme of points? Let's just dive into that question straight away. And so if I have e.g., so this would be, so what is this for Hilb C2n? Question mark. And okay, so I remind you how the Hilb C2n looks like. Hilb C2n looks like this. It's a curve variety. Maybe has C. This is kind of like my vector space W, and then has vector space V. It's n-dimensional, and then their maps going both ways. Maybe I'll call this maps A, B, X1, X2 if you want. And then the relation, the moment map equation, that is the commutator of X1 with X2 plus AB. This is an element in GLV. We think of this as an element in GLV dual. And we mod out, so this is, we equate this to 0. And we intake and take the quotient by GLV. Okay, and then as a consequence, so and the stability, right? Stability. What the stability is? There are two stability conditions you can impose. We can imagine that maybe the stable locus is when things like x1 to the I, x2 to the j times a times 1 span v, and that stability condition. This is one of the two possible stabilities, and this means that this implies B0. So we don't have to think about B. And so, all right. So what would be a map? What would be a quasi-map to that variety? First, so I claim that the quasi-maps. And this is true in general for varieties, that the only thing changes is that all the data I have here right. The data I have here, it's the same data, except now where I had a vector space, I now have, so previously where I had a vector space, I now means I had a group GLV or whatever GLW. And then where I had GLV, instead of a vector space, vector space over a point, I now take a vector bundle over a curve. So let's just try it. So you get vector bundle V. This is vector bundle over my curve C. And then instead of a map from numbers, of course, I'm going to get a map from OC. And then, well, maybe then I should promote this to call it in general if I want this framing space. I also make it a bundle. This is also, this bundle, this varies. And this bundle V, it's a bundle that was associated with the group GLV, and so that is varies in moduli. And this guy here is fixed. And this is acted upon by, so in general, will be acted upon by GLV, by GL, whatever GL. If it's really trivial, by things like so previously this GLV, so if I have some general Nakajima variety, this GLW, this would act on my Nakajima variety, so it should act also on maps to that. And the way it acts is that it acts on this bundle is some copy of trivial bundle, but this has an action of my group. And these are now maps, and X, A, B, X1, X2, these are all maps between. So now Xi, they're now in the homes on my curve C from B to the sections. Okay. And so what does it mean to be stable? What does it mean to have a to have a base point. A base point is where the image is where xi, sorry, x1 to the power I next to the j applied to kind of the image of A, well, fail to generate the fiber of B. But otherwise it's but this should be only finitely many, and so that's in particular if there's since the B was vanishing, has to vanish at all non-base points, that means B is identical to 0. Because so this kind of this implies since B has to at all the points which are not base points, and these are all by finitely many, B vanishes, therefore it vanishes everywhere. You can forget about it. Okay. And now I claim that this is in fact identical to so it's identical. So what does it mean? It means so we have a bundle V plus two operators x1, x2 on it. What does it mean? It means we have, this is the same as we have a sheaf on my curve close, we call C2, right? So this, if I have a sheaf on a curve cross C2, then if I take, so this would be, so my bundle, my V is just the push forward of F to C. Right? So if I have a bundle on a freefold, and I consider push it forward to the base, then I get some sheaf on the, so maybe maybe with some this equivalence requires some extra discussion, which I'm going to be do presently. So we have a sheaf on the freefold. We push it forward to the base, then we get a sheaf on the base together with the action multiplication by the two coordinates. So this is the multiplication by coordinates. So these are coordinates with coordinates. And conversely, if I have that push forward, and I know how the coordinates act, then of course it gives me a sheaf on the whole threefold. Now this guy was a bundle. The bundle on C. Bundle is not any sheaf. Bundle is a sheaf of is a sheaf that's torsion on a curve. Being bundled means locally free, but on a curve is the same as being torsion free. So it means it has no zero-dimensional subsheaves. And then the corresponding three-dimensional notion is again this exactly one-dimensional. So it says pure of dimension 1. Means it has no subsheaves that are zero-dimensional. Because if we had if I had subshapes that are zero-dimensional, that would push forward to subshapes, but this is if and only if statement. If I had some point which supported some subshape, that would push forward to something which has a torsion, which is a torsion object in my push forward. And so then we get, what do we get? We get a map from O of this threefold. That one. This is the map given by all possible. So what are the functions on this guy? These are the functions on. This is like this are the image of x1 to the I, x2 to the j kind of A. And so this is applied to OC. So we start, if you want all functions on this threefold, that's the same if I take the functions on the curve and apply all possible, pull them back to the threefold and apply all possible polynomials on x1, x2. And this is now maps to my sheaf F. And the co-kernel is exactly the base point. Base point. This is the support. So this is where the base point is, where I failed to generate the whole fiber of V by the action of x1, x2 applied to this. And so then we get the Quasimaps from C to help C to N. This is the same pairs. I'll just write PT because there's a space studied by Panaripande Thomas. PT space of the C cross C2, and that this consists of, so in general, this Panaripande Thomas space of pairs is you have a map from O threefold mapping to some sheaf F, which is of pure dimension 1. And the co-kernel is zero-dimensional. So this is for any. This is good. This definition. This definition is good. Good for any threefold. So the reason I brought this up is that this is here the notion of Quasimap really somehow on the nose corresponds to some notion of a three-dimensional geometry. And so then variation is that you can take you can have C2 bundle over so instead of the product. And that has the property that you should allow you don't have to allow the you can twist. So you can, the idea, what would be the idea? The idea would be that this you can twist the quiver data further by automorphisms of X that contains this GLV cross GL edge cross this C star. So we, like, for example, this means, what does it mean that we can make X, so X1, for example, so X1 or Xi, we can be a section from we can be a home from V, not to V, but twisted by a line bundle. Right. So this is saying that if I have a vector bundle, multiplication by that coordinate is not a section of a. So if I have a trivial bundle, we can just multiply by that coordinate. If I have a section of some other line bundle, that multiplication by coordinate, this is the. So maybe all right. So maybe sister bundle. Maybe the way to think of this is if I take C and replace it by sum of two, and so that line bundle would be the dual. Okay. Right. So now where am I in my notes? Not anywhere near beginning, in fact. Right. So maybe I'll conclude that this is so for, again, to summarize. Summary. So if you think of a moduli space of stable maps, this have singularities of this kind of cacti type, and so and something like this on the Graham-Witten side. For Quasimaps becomes something much more manageable, namely just becomes a base point. And this base point depends. So this notion, this is independent of this does not depend on in which stack I put my X, but this does depend on the ambient stack. This does depend on the geometry. And so, which is, good and bad, but it is what it is. It's sorry, I sound like President Trump. I don't want to sound like President Trump. It's a fact of life. So it both has, it also has good features to that. It does depend on that. And then here we took X was more or less arbitrary and smooth. arbitrary means within reason. Maybe projector for affine or something like this. But it's not. Maybe I'll write projector for affine, e.g. plus e.g. projector for affine. To achieve properness, whereas here to achieve properness you need something for properness. We need things like x embedded into, so this is my stable locus, and that it has to be affine over reductive. And so like for example, if we think T star G mod B, that's natural reduction by B, but B is not reductive, so it's not. There's some, if you know, you want to understand the technical. So there are many places to learn about it, but if you want kind of elementary discussion, in Park City notes. So 5 years ago, I gave some lectures in Park City, and there are notes in the book, also online. And then there's some elementary discussion of why is that important here for properties. So, like for example, like I said, this is T star G mod B. It's the obvious realization will fail for the reason that this is a quotient by a non-reductive group. But it's also for abstraction theory. And this already was discussed by Melissa last time, but it's you need to have abstraction theory for that affine variety. So the affine variety has to have a perfect abstraction theory, and that means that this has to be LCI. It has to be. So this is if you want that setup. So why is that? Because if you'd like, well, you need to have some kind of for the deformation theory of maps, you need some kind of abstraction theory, right? So previously we were deforming things to a smooth variety. Okay, we know how to do this. We want to define a singular variety that you need something, and that is, but that's somehow okay. Like so this is the case mu inverse of 0 is okay. This is because that exactly cuts out. What does it mean local complete intersection? It means that it's cut out by as many equations as its codimension, and if we impose the mode map equation, that is the case. So that's like the Hilbert scheme is cut out by exactly the right number of equations. That's a good exercise to check that. If you the point of the point of having B is to have the number of equations be equal to the codimension. And so in the Hilbert scheme situation, we looked at that B, and B is always 0. You think, why do we care? Why do we keep it? But the point is that B, the fact that it comes as 0 as a result of the equation, it's nice, because that means that my abstraction theory is I've posed exactly the right number of equations to achieve the given codimension. So that's it. Right. So I'm out of time now. I want to say one thing is that this, in principle, would belong to a bigger world. Is when you take is when x is a critical locus of a function on a smooth state of a. So sorry, so I take a critical locus, some function on a quotient by reductive group, and this maybe sits on smooth. Yeah, there's the exact technical, what exactly you can do technically, maybe it's not. So this is the way, and then there's some assumptions about, then we need some scaling. Some scaling properties of the function. So maybe call that function, I don't know what to call it, of that function. And so here, in the example of Nakajima variety, that function is you just pair. So you take, you introduce psi in the Lie algebra, and you define the function to be, this is extra variable. And you define the function to be the pairing of psi with mu. And then if you write, the critical locus, well, if you differentiate in all variables, what you're going to get? You're going to get, if you differentiate psi, you're going to get that mu equals 0. But if you differentiate inside the mu, that means that psi mu of x, point x, and then you get the equation that mu of x equals 0, and then the other equation that psi acting over x equals 0. And then for Nakajima varieties, these two conditions plus the stability imply, in fact, that so this plus stability, this implies mu is 0 and psi is 0. So you introduce that extra variable and you get back. So this falls into the general category of things that that Melissa would call p fields. So that's a very important idea, that you can also trade equations for extra variables in a function. So that's this is we're probably not going to go into that generality, just because we're mainly interested. I want to conclude with something. I have to wrap up somehow this course, and so I think I'll just talk about the Hilbert scheme and Donaldson-Thomas theory, where you don't need that generality. It's enough for us to have the virtual class in the generality as explained by Melissa last time, and then. Right, and I didn't get to the pictures at the beginning. So at the beginning of my lecture, I had some pictures. I didn't get to them. Well, I guess we'll start next time with them. Any questions for today?
Could you go to the definition of quasi-maps and maybe a bit above?
Like here or further?
Yeah, here. Yes.
Okay.
So you are saying that for fixed L, like you were saying that I actually, so you wrote something obvious, but you said that this projective space is inside Quasimap, or what?
It's actually equal Quasimap. So if you fix the L, so Quasimap has a data, L plus some sections. And then if you fix the isomorphism class of L, like for example, suppose your target is, for example, it's projective line, doesn't have any interesting line bundles. You fix a line bundle of some degree D, then for that given degree D, you're going to get a projective space, because that line bundle of degree D will have up to isomorphism. There's unique, and that has a C star worth of automorphisms. And so then you look at its sections. So that would be some vector space, and you have to remove the zero in that vector space, because the zero in that vector space is where all of them vanish identically, and then we have to mod out by the automorphisms of my line, but also get a projective space. So
I see. This is
if my domain is to summarize, if my domain is projective line, then the space of quasimaps from projective line to projective space, that is of stable quasimap from projective line to projective space, is some bigger projective space.
okay. Thank you.
More questions?
So I've seen this story in kind of Gromov-Witten theory where there's some wall crossing between quasimaps and Gromov-Witten invariants, and there's some epsilon that parameterizes where you are in this wall crossing. Does that translate to anything in this example you gave for the Hilbert scheme on the sheaf side? Like, is there some kind of understanding of these intermediate spaces in terms of sheaves, or some way to see this?
There are many. So in Downs and Thomas, there are many. I should have right. So this is like a Henry's day. So there's also Henry has another paper. Sorry, you should be giving this lecture. So for maybe I should say something. This is if you wanna quasimaps. So in general, this is a general fact that will we want a quasimaps from a curve C to maybe Hilbert scheme of an ADE surface. This is in general. So this is, you should read Henry Liu. So that is not PT in general. This is some kind of, this is BS. So Brian stands for Brian and sorry, I was Steinberg. Steinberg. Sorry, I forgot the. I'm deeply sorry. So let me look it up. So. Well, okay, maybe I'll put it in the notes when I'm done. So so this is instead of PT in general. So so in general in the Donaldson Thomas side, there are many different chambers, and you get into one of them, and then you might have to might be able to wall cross, or you should be able, but depending on your technical ability, you may or may not be able to wall cross in the others. However, the Gromov-Witten style chambers, that I don't know how to bring in. Like I said, as soon as you allow the least bit of kind of this bubbles to grow in your domain, then I don't know what to do with the self-duality. As soon as you give up on the self-duality, then all the wall crossing terms become really unmanageable, in my opinion. So you can, in principle, you can study that this sort of behavior, and people have studied that, I think. But I think if you're, I think that becomes from the point of the view. So in K theory, people have studied this sort of wall crossing from Quasimaps to Gromov-Witten theory. But I'm not sure we would be able to phrase it in terms of geometric representation theory, because I think that as soon as you let the self-duality go, then it becomes, you can maybe prove some statements, but I'm not sure what you can compute. More questions?
Why? How did we get to condition abstractions are dual to deformations?
Well, because we wanted this virtual structure shift to be like the index of Dirac operator, right? And like the index of Dirac operator on some Keller manifold. That's so we wanted to compare. So what was that? So if I imagine, so the idea would be that the the model situation would be my space deformation space is smooth, and abstraction is some vector bundle. Then this is then the virtual structure sheaf is just like a Kazul complex of the dual of that vector bundle, and for this to resemble a Dirac operator, that vector bundle has to look like the dual of the tangent bundle. But also, this self-duality is used everywhere in this. So when you want to actually prove something, you need so how is one actually computing? How is one actually trying to prove something? One has to if you remember anything from how we construct stable envelopes and the like, there it was really delicate to make sure that things are sections of exactly the right bundle. So that was kind of a delicate balance there. Things were really hanging in the balance there. So if you want to construct, if you want to make some kind of computational elliptic homology, then you need really precise control on the bundles with which you're dealing. And then also in ordinary kind of K-theory, again, we have to make the corresponding argument is some kind of rigidity argument, which says that there has to be some balance between numerators and denominators in some formula, and that balance numerators denominators come from deformation abstractions, and then well, we'll get there. And there it's really important to have a balance. Once that balance goes out of the window, we can't prove anything. I mean, by the methods I'm going to explain, they're really sensitive to being able to achieve a certain. I mean, it doesn't have to be, like I said, it doesn't have to be a perfect balance, but it has to be somewhat. We should be able to twist this a little bit to achieve a perfect balance, but because it means that otherwise, if you're like if we're talking about kind of elliptic homology means, it's there it's very extremely sensitive to that you being a section of exactly the right line bundle, and things have to balance exactly precisely for this to work. And then so if you give up on this, I'm not sure what you want to do. Well, you know, I'm not sure these methods which I'm explaining are powerless in that situation. More questions? All right. Thanks. I thank everybody for bearing with me, and we'll. I hope we'll wrap this course before the summer course becomes like the Christmas course. So this is all for this week, and to be continued next week.